Welcome to this video, produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on the basic principles of mechanics, and in particular on the Suvat equations. First, we need to consider why we're bothering with this at all. If you've got forces acting on a particle which are constant, then Newton's laws tell us that you'll get a constant acceleration as a result. As a particle accelerates, its velocity will change and its displacement from the initial position will also change. And we use various standard letters to represent the variables that arise. So here's the list. S is the displacement, U is the initial velocity, V the final velocity, A is the constant acceleration. Remember, we must have that if Suvat is to be any help to us. And T is the time taken. Now let's look at this represented as a graph. Here we see a representation of what I've just said. The gradient, which is the acceleration on a velocity time graph, has to be constant for a constant acceleration. The initial velocity u is shown as the intercept on the velocity axis, and the final velocity for the displacement we're considering is shown as v, corresponding to the time t. Once again, we have a reminder of the basic quantities on the right there. So, if we're to consider the first step with that, we said the constant acceleration. So here, if we take the acceleration as constant, from the gradient of the graph, we have v minus u over t. v minus u, because that's this distance vertically here, and t because that's the horizontal step which corresponds. So the gradient is the up step over the cross step. That simplifies if you multiply both sides by t into v equals u plus at. Now let's look again at the same graph and see what else we can derive from this. The displacement is the area under the graph. So if we consider that area as the trapezium given by the red trajectory line and the two ordinates and the axis, then we can use the standard formula for trapezium area as half the sum of the parallel sides times the distance between them. Now the parallel sides, the one on the left is u, the one on the right is v, and then we need to multiply the distance between them, t. That's a standard trapezium area, and s is displacement, so s equals a half u plus v times t is our first Suvat equation. Now for the second, I said a moment or two ago that the gradient was equal to a times v minus u over t. I also said that s is equal to half of u plus v times t. Now if you take those two equations together and eliminate t, then you get another equation. Now to eliminate t, we need to express from the second one that t, swapping t and a round, that is to say multiplying by t and dividing by a, we get t is v minus u over a. Now if we substitute that for t in the first equation, then what we'll get is that s is equal to half times v plus u, or u plus v as I have it there, times v minus u over t, over a. Now that is a bit of an algebraic mess, but it can be simplified first by multiplying by 2a on both sides, so we get 2as equals, and we lost the half and the a. So there we are, that gives us this expression which we get by multiplying by 2as, and then if we rearrange that by adding u squared to both sides and making v squared the subject, we end up with the third Suvat equation given there. That one looks a bit more interesting because it's got squares in it. Now let's look again at another way of working out the displacement, essentially another way of working out the area. If we think of the area here as a rectangle with a triangle stuck on top, then we get another expression for s. It's equal to the area of the rectangle, which is u times t, plus the area of the triangle, which is a half, times its base, times its height, which is v minus u. Now that one, if we use the fact that v minus u is equal to at, gives us ut plus half at squared. That's because we had before that v minus u over t is equal to a. So if we replace v minus u by at, that's the equation that we get. There we are. Now let's look at it again, this time by taking the larger rectangle and subtracting the triangle. So in this case, the larger rectangle will tell us that S is equal to Vt this time, minus, and then again we'll have v minus u times t, and then it will be times a half. And that will give us, using the same transformation as before, Vt minus, now we said that A is equal to V minus U over T, so if we replace V minus U by AT, we get a half AT squared, and that's another equation. There we are, summarized. So if we put all that together, what we've now got is a list. So why may we want so many equations? Well, if you look carefully, you'll see that of the various letters V, U, A, S and T not shown, what you've got in each case is an equation which relates all of them with one omitted in each case. So if you don't know the distance, you can use v is u plus at. If you don't know the acceleration, you can use s is a half u plus v times t, and so on. Well, let's look at a problem solved here. A particle moves to the right with a deceleration of 1.5 meters per second squared. Initially, the particle passes the origin with speed 12 meters per second. Find a speed after 10 seconds. Now, if we're working with consistent units, we can leave the units out so long as we check they are consistent and mark on the diagram the information that we've got. We're told that it passes the origin with speed 12. That's telling us that u is equal to 12. We're told it's got a deceleration, so there will be a deceleration in this direction. That's an acceleration in this direction of 1.5. Or if we take the positive direction, it will perhaps be more uniform to replace that by a right-facing arrow and say that it's minus 1.5. We're also told that we want the speed after 10 seconds, so we're interested in what happens when t equals 10. And we don't know exactly where that is, so that's the question we're asking. What happens when t equals 10? So if it's the speed we want, a moment's thought should show that we don't know anything there about distance. So the equation we're going to use is equal to v is u plus at. That's the one which comes up without distance. So there's the information on the diagram. That's the equation we're going to use. So if we substitute, v is what we want to know, so that is equal to 12, and then minus 1.5, because a is minus 1.5, times the time, which is 10. So that's going to give us minus 3. So we conclude, putting the units back in at this point, that the speed is 3 meters per second, and it's to the left. So the conclusion stated there with the units back in, and it's clear that we've interpreted it in the context. Now, a further question, find the time taken to return to the origin. Well, how are we going to characterize the origin? That's where the displacement is equal to 0. So again, we've got the u is equal to 12, and we've got the acceleration is equal to minus 1.5. This time we're interested in the time. So the equation to use in this case is s is ut plus a half at squared. If it's not obvious which equation to use, go back to the list and think which one would actually tell you anything, which one is sufficiently complete with the information that you've got to be able to find something else out. It soon becomes more intuitive getting to the equation right away. So if we do this, then we're going to be able to say that 0 is equal to 12. The velocity u is 12t, and then minus half times 1.5, remembering that it's negative, times t squared, and it's t that we're trying to find. That's a quadratic equation for t. So there we are, we've got our quadratic equation for t. Let's solve it. So we can do that by multiplying by 4. Why 4? Because there's a half factor there and a 3 over 2 in that bracket. So if we multiply by 4, we'll be on the right lines. There we are. We multiply the 12 by 4 and we're left with just the minus 3 in the second term. Then it's a quadratic with common factor 3t. So we finally decide that our solutions are t equals 0 or 16. Now the question was, when are we in a position with displacement 0? We already knew one answer to that question. It was when we started. So not surprisingly, the algebra gives us that as one possible answer. The one we want when we come back, therefore, will be the 16. So t is 0 is the initial time, so the time to return to the origin, back in context, 16 seconds with the units in. Now finally, the total distance travelled in the 16 seconds. Well, again we're going to be saying that we've got an out and return trip. We don't know how far out we've gone. If we ask for the displacement when t equals 16, then that's not really going to be much help to us, because we know that we're back where we started. S will be 0. What we really need is to find the displacement at this end. What's the displacement there? Now to do that, we have to ask ourselves how that end of the journey is characterized. It's where v equals 0, where the velocity at time t is 0. So if we use what we know, we'll use v equals u plus at again. And this time we're interested in that would find us the time when we get to the far end, but we want the distance. So it's not that equation, it's v squared is u squared plus 2as that we want. And if we do that, then we'll get that the distance 0 is the v, u squared is 12 12 is 144. Then minus 2 times 1.5 is minus 3 times the distance s, and that will tell us that s is equal to 144 over 3, which is 48. So that's the distance from O to A. So our distance back again altogether will be 96 meters. Now I've done it a different way here. I've said apply v equals u plus at to find the time to the far end. If you do it that way instead, then you use v as u plus at, you've got 12 minus 1.5t, giving you t equals 8. Once you've done that, you can use another of the formulae with the information that you've got to find the distance, and that works out as a half times 12 plus 0 times 8, again 48. So that's in 2 steps. It's an equivalent process. It gives you the answer in a different way. So finally, the conclusion is that the total distance is 96 meters. That's 48 meters each way. And there we are. That concludes this video presentation. The next in the same series on basic principles of mechanics focuses on resolving. I hope to be with you later to explore that.